the first application of calculus we'll be doing is the analysis of functions in order to find local maximum and local minimum points. So a maximum is where a curve is rising and then turns around, or a minimum is where it's falling and then it starts to turn around and go back up again. So the simplest function that has both of these features is a cubic. So cubics, you should have sketched a few of them in advanced functions. Do this sort of thing, and then they turn, and then they turn, and then they head back up. Well, that is a terrible sketch, but it it will demonstrate the point for now. So the trick to this is that at this particular spot and at this particular spot, which you've never been able to find precisely before, the curve has been decreasing, stopped decreasing, and started to increase. And at that place, at exactly that spot, the maximum or the minimum, it is neither increasing nor decreasing. So if you were to draw a tangent at that place, those tangents would be flat. So if you keep in mind that the derivative, by definition, is the slope of a tangent to a curve at any particular place, you could identify that location by solving any place where the derivative of this function is equal to 0. So that will be true there, and it will be true here as well. There is a third place, third way this could show up. I'm going to have to try and draw it. It's a little touch more exotic. Is if you had a cubic that came up, and instead of having a max and a min, it transitioned like this. That place as well, if I were to draw the tangent, would be completely flat. So what I have generated here then are three different features that occur when the derivative is equal to 0. One of them would be a maximum, one would be a minimum, and one is called a saddle point. Now, why a saddle point? Well, if I take this curve and I draw you a stick figure who's sitting on it, holding on because it's some sort of horse or dragon, whatever you think that is. They're sitting in the saddle right there. So now that you've got an idea of what we're after, I'm going to start with a cubic, and I'm going to take its derivative, and I'm going to use that derivative to find the locations of its max min points, if it has any. And then we'll try it on some more exotic like composite functions. So I'm just going to clear this off, and then we'll try the cubic. So this cubic, it may max and then min and then take off. It may have a saddle point. I don't know. I have to actually do some calculus on it to try and do the analysis. So the idea is that at a maximum or a minimum, so let me write that in, at a max or min, max slash min slash saddle, whatever words you need to put in there to get this idea across, the derivative of this thing is equal to 0. So I'm going to have to take the derivative of this cubic first. So let's do that. This thing is m, so I'll be finding dm by dx. That would be 1/3 of a derivative of x cubed would be 3x squared minus 3/2 of 2x to the 1 minus 18 times x to the 0, and then plus 18 times 0, because there is no function of x back there, or if you choose to, you can just not write that in. Cleaning this up, 1/3 of 3 is just 1. 2 times 3/2 is just -3. And I've got a -18 here. And that piece is gone. So do you notice that my cubic here has a quadratic derivative? So that's sort of telling. A cube can generate up to 3 answers. And so this thing is going to find your x-intercepts, which you should have done in advanced functions. You find one, you divide it out with polynomial long division, and then you factor to get the other 2. So a cubic, if it does this, let me just quick sketch. There's your axis, and it does this. It can have up to 1, 2, 3 x-intercepts. So a cube can return all 3 of those. The quadratic only has 2 answers. Well, this thing only peaks or troughs up to 2 times. So that makes sense, just algebraically. Get that cleaned off. So in order to actually find those places where the max and the min occur, I'm going to have to take my derivative and set it to 0. So 0 equals x squared minus 3x minus 18. And the reason you're doing that is the curve is flat at a max or min. So I mean, you could have asked, when is this thing have a slope of 1? When does it have a slope of 1? You just put a 1 there. Or you could ask, when does it have a slope of 10? You put a 10 there. The only reason we're putting a 0 there is that the max mins, like the interesting places where it turns around, are where it's flat. So I'm going to choose that particular slope, and I'm going to ask the algebra to tell me all the values of x for which that is true. So I'm going to look at this thing and think if I can find 2 numbers that multiply to negative 18 and add to negative 3. And so I think I can do that with just factoring. So 0 would be x minus 6 and x plus 3. So case 1 here. If this times this equals 0, either this equals 0 or this does. Possibly both, depending on how the numbers work out, but that's the idea behind cases. We're going to be using this little structure quite a bit. So I end up with an x equals 6 and an x equals negative 3. Therefore, there are max slash mins when x equals negative 3 or when x equals 6. Now, I don't know if it's a maximum or a minimum. I just know that the curve is flat at those 2 places. So I'm going to have to do a little bit more work to figure out which one's a max and which one's a min. And it's not hard work. The issue is that I don't know how high vertically these are. I know where they are horizontally, right? One's at negative 3 and one's at 6, but I don't know how far up to go. So once I spit these values out, I'm going to have to get a y value, and the way you do that is take your x and plunk it into the original function. So I'm going to have to put this into m and get an answer, and then I'm going to have to put this into m and get an answer. So I'm going to clean that off to do this. Alright, so m at negative 3 would be 1/3 of negative 3 cubed minus 3/2 of negative 3 squared minus 18 times negative 3 plus 18. So I'm just going to grab a calculator and I'm going to do that. And using proper calculator technique, I'm going to do it 1 term at a time. So 3 cubed is 27, and 27 divided by 3 is 9. Negative 3 squared would be 9 times negative 3 is negative 27. Negative 27 cut in half is negative 13.5. 3 times 18 would be 30, and 24 is 54. plus 18. So 54 and 18 and 9 minus 13.5 gives me 67.5. So I put in negative 3 for the x, and I got 67.5 for the y. So I have negative 3, 67.5 as one of my points. I'm going to do the same thing, but I'm going to use my x value of 6 instead. So get rid of that, get rid of that, get rid of that, get rid of that. And in goes my 6. Alright, 6 times 6 is 36, times 6 is 216, divided by 3. I'm going to trust myself on that one. 72. 6 times 6 is 36, divided by 2 would be 18. 18 times 3 is 54. 6 times 10 is 60, and 6 times 8 is 48. That's 108 plus 18. So 72 minus 54 minus 108 plus 18 gives me negative 72. So I have 6 comma negative 72 as one of my max min points. Okay. So I'm going to try and sketch this. I'm going to have to use a funny scale on my y because these numbers are so big. I'm going to clean this off and then we'll give that a try. Alright, so now that I have the axis on there, I just went 1 for 1, so that would be 6 on the x, and there's negative 3. So I apparently have a dot at negative 3 and 67.5. So that's about here, right? Negative 3 on the x and there. When I curve sketch, I like to put this in as a dashed horizontal line. Because I know that I either come into that thing like this, right? Come in, graze it, and turn away. Or I come in from above, graze it, and turn away. My other one is at 6 on the x and negative 72, which is about here. Now there are going to be some x-intercepts in here, and I'm not going to bother finding them for this particular example because we're only finding max mins on this. Once we get to curve sketching, you'll need to find all of those features. But just to keep us sort of on, this was plus 18 was the last bit there, so I can put my y-intercept in. So with the y-intercept here and an approach line there and approach line there, the only way I can draw this is to come up from that, crest, and then come back down, and to come like so, trough, and then go back up. Connect these in a little darker. So now that I have it drawn, this one at negative 3 is clearly a maximum. It's the only way these features could work. So I can jot that in, max. And then this thing here is clearly a minimum. You might have guessed that by the fact that this one is positive and this one is negative, right? One is much higher than the other, and that's fine for identifying which ones are maxes and which ones are mins. If these had been saddle points, the only way you'd be able to see that is by actually sketching it, to see that the thing was rising and then flattened and then continued to rise after that. So now that we've done it on a cubic, I'm going to try it on 2 different composite functions so that you can see that the operation is the same. I'm not going to bother sketching them because we need all of the pieces in order to get a good picture. But I can walk through the process of the actual calculation. Right. So to find maxima and minima, I have to take the derivative of the function and then set that derivative to 0. So I'm going to need df by dx from this particular function. It is a function multiplying a function, so I'm going to need my product rule infrastructure. Let me jot that in there. This is not a function in a function, neither is that, so I won't be needing any chain rule. So I just have to do the derivatives now. Derivative of a radical is 1/2 x to the negative 1/2. Leave the e to the x alone. Leave the radical alone. And the derivative of e to the x is e to the x. So here's where things get a little tricky. This was fine when you were doing derivatives, and that is the answer. But it's not particularly useful to me at this point because I need it to be in brackets that I can use to build cases. We're going to have to do some factoring. So the first thing I notice is I have an e to the x in both of these terms. So I'm going to pull that out. df by dx equals e to the x. What that leaves here is 1/2. And then x to the negative half, it's 1 over, because it's negative, and it's square root x, because it's 1/2, plus this radical here. Okay. Now, I have a fraction, adding a fraction, so I'm going to create a common denominator so that I can collapse those fractions into 1. This side has a root x in the bottom that this doesn't have, so I'm going to put that in there. That's an extra factor of root x in the top. And I need a factor of 2 in the bottom, so in it goes. My next line then would be df by dx equals e to the x. 1 times 1 is 1, plus 2. A root x times a root x is just an x, all over 2 root x. And I can further factor that by writing it as an exponential part, the rational part, rational radical blend part, and the linear part. Now, why would I do that? Well, here I can see that I have 3 things multiplying each other. So in order to check my cases when I set this to 0, there's going to be 3 cases I have to check. Speaking of which, to get my maxima and minima, once I do the derivative and tidy her up, I have to set it to 0 and solve. So case 1, case 2, case 3, e to the x. Can this equal 0? Or can this equal 0? Or can this equal 0? Those are the 3 things I'm checking. This has an asymptote running along the x-axis, so this is actually impossible. But if you want to convince yourself of that, you'll need the anti-function for e to the x, which is ln. So x would be ln 0. And if you try that, you get error. This one here, 1 divided by 2 root x. Well, you can't get 0 through division. It's not possible. But if you want to convince yourself, perhaps you'd like to cross multiply. 1 equals 0 times 2 root x. And 0 times 2 root x would be 0, and this is impossible. So that's no good. Case 3, I'm going to kick this 1 to the other side. And I'm going to divide both sides by 2. Now that one actually works. It gave me an answer that's a number, that's not an error or something that's impossible. So here we go. I have found a turning point in this particular function. Is it a maximum? Is it a minimum? I don't know. And I'm not going to find out until I actually have the x-intercepts, points of inflection, and vertical or horizontal asymptotes to actually get a sketch. for now, I'm just going to use this x to find out where it is exactly. So I have the horizontal information. I need the vertical information. So to get the y value, I take this and I plunk it back into the function. F at negative 1/2 would be square root of negative 1/2 e to the negative 1/2. So I put that in the calculator and I try to work it out, and I will find out that this thing is an error because you can't square root negative numbers. So even though there was a potential turning point, that turning point failed because of the domain of one of the pieces of the function. So if that happens to you, what you write then is, therefore, there are no turning points. So you might be annoyed that we did all that work to find out that there are none of them. But knowing that it can't do that is almost as useful as knowing that it can. If you were trying to sketch this, right, you start doing this kind of thing, and then maybe you tried to draw a tail, well, that's forbidden, because it's not allowed to do that. This function has to, if it's increasing, continue increasing forever, because there are no places for it to turn down. If it starts decreasing at the beginning, it can never start to increase again, because it's not allowed to turn. So that's what happens if you have one that falls in a domain error. I have one more for us to try, and hopefully we can find a max min on that one. So again, to get max min points, I have to take a derivative and set it equal to 0. So here we go, dg by dx. This is a function in a function, so I will need my chain rule infrastructure. Working from the outside in, the derivative of a ln is 1 over whatever's on the inside. And then the next layer in is an x squared plus 1. The derivative of that is 2x, just 2x. 2x plus nothing. Right? Derivatives of constants are just 0. So I have a function that is split into two different pieces already, which is handy. I have this linear piece, and then I have a composite rational kind of piece. In order to find maximum minimum points, I have to set this thing equal to 0 and find all of the x's that make that true. And I can see by this setup that I'm going to have two cases, either this equals 0 or that equals 0. Pop them in there. So case 1, case 2, either 1 over x squared plus 1 equals nothing, or 2x equals nothing. So in the first case, you cannot get 0 by division. It's not possible. But to convince yourself, you could do a little cross multiplication. And 0 times x squared would be 0, and that is impossible. Here, divide both sides by 2, I get x equals 0. Now that, like the last example, was a perfectly valid number. It's not going to infinity, it's not giving me an error. So I potentially have a turning point when x is 0 in this function. So the only thing left to do then is to put this back into the function to get the y value. So g, when x is 0, would be the ln of 0 squared plus 1. So g at 0 would be the ln. 0 squared is 0, plus 1 is 1. And if you get your calculator out, ln of 1 is 0. So there we go. This one did not produce an error. I found an x in one of these cases that would set the derivative to 0. And when I plunked that back into the function, I got a perfectly reasonable answer. So what I have deduced then is that g of x has a turning point at 0 on the x, 0 on the y. Is it a maximum? I don't know yet. Is it a minimum? I don't know yet. It could be a saddle point. I don't know that yet. I need all the other features about this function on a grid before I'll be able to make that determination.